So I'm John White. I work for a company called AiTech. We're located in Los Angeles, California. And we primarily make space electronics. We've been doing 3U size computer boards and peripherals for small sets generally. And we do the boards and the systems, and we fly from everything from LEO all the way up to the Lunar Gateway. We have a communication system on there. Our customers range from most of the space customers you guys have seen. This is more US-centric than it is European-centric, but this is a snapshot of the customers that we typically sell to. But now we're engaging on a CubeSat, which has a customer that doesn't want to be named. And what we thought is that we wanted to make a CubeSat that could go for 3 years. Our mission goal is to have a 3-year CubeSat at 450 kilometers orbit, circular orbit. We want to be able to maneuver for, get out of the way of space debris or avoid space debris. We wanted to be able to maintain, like I said, 3 years, and then be able to deorbit at the end of the 3-year period. So if we do a little bit of calculation for that altitude, at worst case, what we see is that we can get, worst case would be like 2.5 kilometers per day deorbiting. Of course, that's a lot to compensate for with a thruster, but roughly we need about 170 micronewtons per minute in order to, for a thruster, capable thruster to be able to maintain orbit. So what we did is we went out and we did a survey, and I removed the supplier's name. I'm just going to call them supplier 1, 2, and 3. And you can see here are a list of some of the features that we were interested in order to determine whether or not we'd be able to maintain our 3-year orbit. And just like any engineering puzzle, there's not an easy answer. It really depends, from this chart, what the takeaway should be, it really depends on what your mission needs are. If you want low cost, there's a low cost supplier. If you want the most thrust, there's a most thrust supplier. But it comes with trade-offs, and your mission is going to dictate what choice that you choose. So to get more specific on the different thrusters that are available, this happens to be a thruster that you'll hear more about a little bit later on. I wrote down what some of the performance criteria are. But what is of interest to us was that it had a low input power, so that we didn't have to have a super big solar panel to run it or a big battery. And the power to thrust ratio was favorable for our situation. This is another supplier that we looked at. What we liked about it was, again, that it had an optional range of power, that we didn't have to use the 20-watt max, but had something that was kind of in between. The maximum thrust was very good, but the total life wasn't as good. And then this thruster, this is the least expensive thruster, so that was very attractive for us. It's kind of almost an order of magnitude less than the other two, but you can see that its thrust per power ratio is on the low side, and the maximum thrust is on the low side. So to achieve our 3-year plan, or 3-year goal, we really were having a problem like I say, none of those thrusters were the clear, easy answer. In fact, none of those thrusters got us to a 3-year mission. They fell short. The other thing that we had to look at was, how do we actually use the thruster to maintain our orbit? And the typical way of doing that would be using a Holman transfer orbit, which is basically, if you're going between 2 circular orbits, you have an elliptical thrust that moves you into the next orbit. And so you thrust up, and then you counter thrust once you get to the place that you want to be. But to do that would take a lot of energy, and it was more than we actually had the thrusters would not allow us to have that much burn time for a 3-year period. So we, actually I should say Jen, who's sitting here in the middle of the room. Jen is working with us, and he said, hey, why don't we just do a little push at at 2 places in the orbit so we maintain circularity. And so this image is actually from him, and he showed this, and I said, yeah, that looks like a good approach. So we're going to do that. That's what we're going to try to do. And with the thruster that we've chosen, we think that we're going to be able to extend our life by about 180 days. So how long does that mean? Well, it doesn't mean that we're going to hit 3 years. We're going to get just over a year at the 450 kilometer orbit. And then we had this other crazy idea. If you guys are building PocketQubes, you already know that room for reaction wheels and magnetorquers, there isn't a whole lot. There's just not a lot of room in the capacity. So we thought maybe we could use the thruster in a way that would allow us to do the attitude control. So we considered having the thrusters at 45 degrees to the axis. I tried to show that with my little drawings and sketches up above. But with that, we were able to have pitch roll and yaw control. And assuming the 1.5 kilogram satellite, which I know is on the heavy side for a picosat, and then we were a minimum of 90-degree movement, plus and minus 90-degree movement in each orbit. We could actually go for about 2 years with one of the thrusters that I showed. Problem is that even that's only just steering. We still need to maintain orbit, and so we still don't hit our 3-year mark, not even close. So using the 45-degree angle thrusters, we could do the station keeping, or we could do thrusting by powering them all at the same time. That would give us a propulsion, forward for station keeping. But if you combine the two, it only ends up being less than 90 days of service. So that really wasn't that. Although I thought it was a good idea to start with, and analytically didn't pan out very well for us. We want to maneuver to avoid space debris. I think the takeaway there is that if you have space debris and you have to maneuver, but it's not going to mean, it's going to mean that you're going to lose some of your orbit station or your station keeping time. And I think a maneuver could reduce by days rather than just a fraction of a day, because you'll be using max thrust in order to get out of the way of something that might be impeding onto your orbit. Again, I mentioned that our goal was to maintain orbit for 3 years. Well, that's still a goal of ours. We hope thruster technologies continues to improve. I will say this, that in the 6 months that we've been looking at thrusters, we've gotten improvements in some of the numbers, and some of the data that I shared today is actually better than it was 6 months ago. So there is a trend of improved thruster efficiencies, and I think that maybe in a year, maybe 2 years, we might actually get our 3-year mission, and then be able to de-orbit at the end of its life. Well, at a decay rate at 450 kilometers of 2.5 kilometers per day, it's questionable whether you need to force that issue. It's going to happen anyway. And I think that a lot of people that have already flown have already found out that that's the case. But there's a presentation just yesterday talking about ESA's new requirements for deorbiting even quicker. So that would mean additional load demand from the thrusters, and that, of course, is going to take away from your mission. And basically, that's my conclusion, is that the thrusters technologies is improving. I think that in the future we'll be able to achieve our 3 years, but today it's not quite there. And that's all I got. Do you have any questions?